So I'm Uri Peskin from the Technion, from chemistry. And the talk I will present, the different talks actually I will present are related to the work of Daria, who is now postdocing at Heidelberg, who was in my group. Roy, who is now in the industry, finished his PhD. And Meital, who is a postdoc, Marie Curie fellow, postdocing at Princeton. So this is Haifa, by the way. You have to, so you see the bay, the Haifa Bay. We are on the Carmel mountain. This is Haifa by night. It's behind Temple. So those of you who haven't been, and I know many of you have not been in Haifa and wish to visit, let me know. Perhaps we can arrange something. Okay, so my talk will be about coherent charge transport through molecules in a dissipative environment, and in this context, it's very related to the content of this meeting, this workshop. Some motivation comes directly from the main focus of this conference, the discovery of, or the measurement of quantum bits in electron energy transfer in photosynthetic units, and the possibility that was raised that the wave-like characteristic of the energy transfer can explain its extreme efficiency. We heard a lot updated work about this idea. Another motivation to study quantum transport in molecule in particular comes from another field which I'm working in, and that's the field of single molecule electronics. A molecule is connected to two leads, essentially two macroscopic leads, and the current is measured. And whether quantum transport plays a role here is really an interesting and a hot question. I will just quote one recent results of our colleagues from Erlangen, this is an experimental work measuring the IV curve, the current voltage curve at different temperature, showing that increasing temperature actually increases the current. And the idea here was that you have interference, destructive interference in this case, between different pathways of charge transport along the molecule, where upon hitting you destroy the destructive interference and you actually enhance the current. So quantum transport per se, namely that has to do with interference and phase conservation, is really related also to this field. So the outline, I will try to, everything I will say will try to somehow relate to the question, can coherent phase-conserving transport be observed and controlled in a dissipative molecular environment? And I will actually tell you three stories. The first part is about ballistic transport through DNA molecular junctions. A second part will be about a coherent bichromophoric single electron pump. In your context, this is related essentially to exciton splitting, if you're interested in this. And finally, an example of reservoir control of quantum transport in a multi-chromophoric molecule. So all these will be theoretical works, which we do, and I hope you'll find them interesting. I know this is an after-lunch talk, so I will take the opportunity to wake you up between these lectures. So statistically, maybe one of them you'll be awake. So, okay, so let's start with the DNA story. And why worry about quantum transport through DNA? This is seems very different from the system, this photosynthetic system. And here we talk about charge transport, not energy transport. It's related to the biological importance of charge transport through DNA. Both in the relation of damages to DNA, which involves slow electron scattering and charge transport through the system, which leads to mutation damages in the DNA. Charge transport through DNA was, in the biological context, was associated also with the enzyme that repairs damages in the DNA in the organism. So it's very relevant from the biological perspective. It is relevant from the molecular electronics perspective. This is a highly known and documented molecule, very robust, easy to synthesize with different properties. And it was proposed and still is proposed as maybe a potential candidate for doing molecular electronics, so single molecule devices. That's another reason to be interested in this. And maybe the most important thing, I think also in the context of this community, and certainly for my own personal interest, is the physics. What is the mechanism of charge transport through this system? It's really a complex system. There's no chance to do anything ab initio here. And still, there are many speculations about what the charge transport may be, what is the mechanism. Any transport mechanism that you can imagine was already associated with DNA in some conditions, because it's really a messy and a complex system, actually a zoo of systems. One DNA is not as another DNA. So there's activated hopping, thermally activated hopping, tunneling, polarons. And what I will talk about today is, can we find experimental conditions to measure coherent ballistic transport through such a system? Our motivation, specific motivation to look at DNA came from these experiments from a few years ago, from the Barton and Knuckle groups. And what they did is they connected a DNA molecule, a double-stranded DNA molecule, to two electrodes, carbon nanotubes, covalently. And they measured current. They actually didn't measure IV curves. They applied a gate and measured the gate under small bias, the current under small bias. But that's what they did. And moreover, they could control the connectivity of the electrode to the system. So if we regard just this DNA system as a network, a molecular network, they could connect to the network differently, chemically. Sometimes to the same strand. It's a double-stranded structure, right? So sometimes they could connect covalently to one strand, and sometimes in a diagonal form. So one electrode to one strand and the other to the other. And they measured what they measured, currents as a function of gate voltage. And they could not determine any significant difference between the connection strategies. I was intrigued by this, and we started to look into this, because whether the transport should be sensitive to the connectivity to your network or not really has to do with the mechanism you assume or you expect. And we started to look into it. So how to approach this very complex problem? The simple picture. Let's look for a minimal model. The simple picture that's the common wisdom about charge transport through DNA is really a hole transport. You take an electron out, you have a hole, and then you have migration of the hole. Again, the common wisdom is that the charge migrates through the pi-stacked nucleobases. So these are nucleobases, they are pi-conjugated systems. In the three-dimensional structure, they lie one on top of the other. And the p orbitals sort of overlap. This is known in chemistry as pi-stacking interaction. And the charge transport is considered to go through these pi-stacked nucleobases. Okay, you see here an artist view of what is believed. Each nucleobase is a unit that has different ionization potential. So its energy per hole is different. Guanine, one of the 4 bases that compose DNA, is the most stable site for a hole. And the others are as follows. You see, so you have a landscape in this helix, in this double-stranded structure. You have a landscape of different wells, potential wells for holes. And the transport is really some walk quantum or classical. That's another issue we will talk about along this landscape. So that's the simple picture. To model this, the most, again, the minimal model approach is to have some tight binding model. So each nucleobase will have an on-site energy, and the coupling, this pi-stacking coupling between bases will be some hopping term, just as you have in your tight binding models. And luckily, so each nucleobase in this picture is only represented by its highest occupied molecular orbitals, where the electron is taken from this orbital, we have a hole. Lucky for us, people parameterized using ab initio these tight binding models for DNA. These are works by Joshua Jortner from Tel Aviv and others, who really parameterized the on-site energies and the hopping for different DNA sequences. In fact, they did a serious job in the sense that the three-dimensional structure of DNA was actually encaptured, I would say, or captured within the two-dimensional ladder model. How come? They considered that if you're, for example, a T nuclear base and you have neighbors G from the left and C from the right, you have a different on-site energy if it's reversed, if G is from the right and from the left and from the right and C is from the left. This is because of the three-dimensional helical structure. The overlap between the bases is different. The on-site energy is different. So this model actually has more information than just a two-dimensional one. So this was done and known, and we wanted to mimic the experiment that was done that I showed you about the connectivity and to study the mechanism. So we have to put electrodes. To put electrodes, we used a so-called semi-elliptic band model, or if you will, just a one-dimensional semi-infinite chain of lattice sites to have some model for a band, and we could set a chemical potential to the two electrodes, and what we want to calculate is the current. To make the simulation, we had to set some chemical potential in the absence of bias. We put that about 1 eV above the highest energy modeled in the system for a hole. We put some coupling, some effective magic number for coupling, which is 75 milli-electron volt, is certainly within the order of magnitude of the correct numbers. We don't know, nobody knows the correct number. Playing with it changes, of course, quantitatively, but not qualitatively, what I will discuss. So these are somewhat arbitrary choices. And now we need to calculate current. To calculate the current, we just use the Landauer transport equation. Now here is a very important, first important comment. We divided our study to 2 steps. In the first step, we said, let's assume that everything is perfectly coherent. So in your language, we don't have a bath. Okay, nothing moves. We freeze all nuclear degrees of freedom, all solvent degrees of freedom, and just consider this electronic structure problem where we have one lead with one chemical potential, another lead with another chemical potential, and a tight binding ladder parameterized according to DNA. And let's see what the current would be assuming just coherent scattering. This is essentially the Landauer formulation. It's for non-interacting elastic scattering only. And it really, the picture is, let's calculate the transmission, the scattering amplitude to go from left to right, and integrate over all energy within the Fermi window of the electrode. This would, what I would refer to as purely coherent transport. So doing this, okay, not doing this, let's go back to the experiment we want to mimic. So we have a very particular sequence and different connectivity. We replace the experimental cartoons with a theoretical cartoon. So now this is our model. And we can play with all kinds of connectivities that the experiment did not reach. So all possible ways to connect to this molecular network. So we did a calculation for the experimentally measured sequence, and we got some numbers. These numbers refer to what would happen if you would include all these highest occupied molecular orbitals, which are coupled within the Fermi window. So it's essentially the maximal current that you can get. And these are the numbers. And let's point out 2 things. Assuming this coherent transport, first of all, there is no clear dependence on the connection strategy. For example, here there is a diagonal connection to the network, 1.77, 10 to minus 5. Here is a direct connection, more or less the same number. No clear connection between the number for the maximal current and how you connect to the network. That's our...
That is 10 and minus 7.
Yeah, that's the second point. You are awake, I'm very glad.
And this was one of the tricks you...
Yeah, just to keep you awake. The other thing, which is... We were embarrassed to put an IV curve here, because these are absolutely, these are zeros. You see, the currents that are measured in the experiment are on the order of, well, how am I going? Anyway, oh, here it is, sorry. Tens to hundreds nanoamperes. We are 7, 8 orders of magnitude below that. So zeros, essentially zeros. Embarrassing, so nothing happens. With this frozen picture of elastic coherent transport, nothing happens for this sequence. So what is going on? Of course, this doesn't contradict the experiment. They, obviously, in their experiment, this was not the mechanism. So they measured some currents, and OK.
What about this? First, it doesn't matter. They're not symmetric. You expect doesn't matter which side current from left to right or right to left.
That doesn't matter. This is.
When you get 10 minus 7, 10 miness 5. Why you do have different?
OK, I will get into it. I will get into it. There is a difference still between the different connectivities. If you want, I can answer it now just for the expert. The orbitals that are associated have different amplitude on the contact site. Yeah. So if you connect like this or like this, you will get a different current.
Because it's a disordered system.
Yeah, exactly, exactly. So you know the story already. We decided maybe they just did the wrong experiment. Well, in what sense? They used some sequence which is at first sight rather random. Look at it as a word. So it's a TC, ATGT, something disordered, very random. And what would happen, there are many, many other sequences, other DNA molecules to choose. Let's take an ordered one. An ordered one, a poly-GC. If we do that and repeat the same exercise, so it's the same level of theory of the ab initio fitting of tight binding model, the same electrode, the same chemical potentials, the same model for the band, and so on. The currents immediately, just by replacing to an ordered sequence, they jump to the experimentally measurable values. This was not measured, this sequence, but yeah.
So just to understand, so now you put completely ordered system.
Yes, yes.
So the same energies, the same coupling.
Yes. Well.
Slight just a bit of interchange between up and down.
Exactly. Only actually there is an Okay, you are right. Basically, it's an ordered system. Okay. Absolutely. I will get to it. I will get to it in details. So immediately you see a jump of few orders of magnitude in the current, and moreover, you get very nice sense of the effect of connectivity. So for diagonal connection, you get hardly, well, very small current. If you go directly, so you couple the two electrodes to the same strand, you get one step in the current. And if you couple to both, you get a double current. So suddenly things make sense. What is happening? Those of you who come from solid state physics know about Anderson localization, disorder transition. But if we just take the Landauer formula, and this is a kind of a brute force machinery, just scattering calculations. But if we do perturbation theory, we can see that the current, the formal Landauer current, it can be written, OK, as long as the coupling to the electrode is weak, which is very important, and it happens in this system because there are organic linkers, linking group between the nanotubes and the DNA. I won't go back to it, but it's there if you noticed. So in this weak coupling, the current can be written as a sum over molecular orbitals contributions. What are these molecular orbitals? If we couple our nucleobases with the tight binding coupling, we get extended states, essentially. And the current is a sum over each and one of these extended states. And what really gets here, the contribution of each state, relates to the amplitude of the wave function on the two contact sites. So this is a very simple perturbative interpretation or limit of the Landauer formula, but you can get it smoothly within perturbation theory. So the name of the game is to obtain coherent transport, you need to have each orbital that contributes to the transport must have a weight on the contact side to the left and on the contact side to the right. If one of these weights goes to 0, 1 over the contribution goes to infinity and the contribution goes to 0. So you must be extended the localized state. And indeed, in our system, let's take this ordered sequence. We have a poly-GC. we have essentially, I will not go in too much detail, just give you the last result. It may be transparent to most of you. We essentially have two kinds of orbitals, of extended orbitals here. One are associated with the C nucleobases. So these orbitals are extended on the structure. The other kind of orbitals are G orbitals. This is just because there's a big difference in the on-site energy between the C and the G. And the couplings, the electronic couplings are small. So we have essentially like two bands. In the solid state language, we have two bands, a C band and a G band. So it is very clear now, if we couple diagonally, so one electrode to C, one to G, there's no single orbital which takes us all the way here. But if we couple directly to G and G, or to C and C, we get contribution to the current. Just to emphasize what was done in the experiment, taking this, replacing back this ordered sequence with a disordered sequence, the orbital look like this. It's a disordered system, you have localization, and the coherent ballistic transport goes to 0. So far, no dissipation, so let's summarize. Ballistic transport through DNA should be sensitive to the connection strategy and enhanced for order sequences. But what about dissipation? Okay, so we need to switch gear and put some dissipation. So our model now will include, in addition to the leads, the electron reservoirs, also nuclear bath, just a harmonic bath in the way we heard about in this conference many times. So our transport problem through DNA will be coupled to electron reservoirs and also to phonon reservoirs. Our Hamiltonian will now include the system itself, the leads, and the nuclear degrees of freedom. The system Hamiltonian is just the tight binding ladder, now written in second quantization. The nuclear Hamiltonian is as following. We introduced an uncorrelated nuclear motion, so each site is associated with some local modes, which are hindered by hopping from one site to another. So the model, you have as many different paths as the number of nucleobases in the model. So this is our environment, the structure of the environment. And we have, okay, just again, this is, I just said it, and very briefly I'll go over it. It's a collection of bosons or harmonic modes with linear coupling to the system. In principle, one has a spectral density depending on the DNA itself, the solvent, etc. For our calculation, we use the celebrated ohmic bath model for the spectral density of the nuclear bath. For the leads, again, we use a semi-elliptic band model. Again, written in second quantization, just like we saw today. So this is the lead Hamiltonian, and the coupling is linear in the sense that there's hopping, one electron hopping from the molecule to the electrode and vice versa. So this is the lead Hamiltonian. And now we will change strategy. In order to have dissipation and inelastic processes, we must leave the Landauer elastic coherent transport approach, and we move to a density matrix framework. So our system is now coupled to several reservoirs. Two of them are fermion reservoirs, grand canonical ensembles at equilibrium with some chemical potential. The phonon reservoirs are just thermal boson reservoirs. And what we are going to assume, and here I will say the following. We're in the weak coupling regime, and I'm proud of it. Okay? So I'm not attempting to do anything in the intermediate regime. It's really, we will assume for the discussion, weak coupling to the electrodes, which I already mentioned, and also weak coupling to the nuclear degrees of freedom. In this case, we will use Redfield theory to handle the reduced system. Our reduced system is represented, as usual, in the eigenstate basis. So these are the molecular orbitals that I mentioned before. And we want to follow the reduced density matrix using the Redfield equation of motion. I don't have to dwell on it much to this audience. So we have the coherent evolution, and we have the dissipative term, which is derived from the microscopic model that I showed before for the fermion reservoirs and the phonon reservoirs. So this is what we're solving. To get steady state currents, we can actually do the extra secular approximation, which was discussed a lot also. So to get steady state currents in the weak coupling regime, coherences indeed do not matter. So we can just follow the population and in fact follow the infinite time limit of the population following Pauli rate equations. So the picture we have some manifold of molecular orbitals, and the interaction with the reservoirs, electron and phonon, can enhance transition between them, population transitions. Some transitions will be associated with charge transfer. These are these rates. You see electron hopping in and out. Some will be energy transfer, so interaction with the bath. These do not involve exchange of electrons with the leads. And if we want to get the current, what we can do is just count per unit time the number of electron hopping to one of the leads and extract it from the steady state density. So this is about the methodology that we use. Let's see some results. Let's take a short poly-GC sequence and connect to it diagonally and directly, this time with dissipation. So eta is the reorganization parameter, if you will, or the dissipation strength. And what you see is that even though we have dissipation, conductivity still matters. So this is the current you obtain for a diagonal connection. This is the current you would get for direct connection. What is going on in more details? What we can do easily in theory is to switch back the dissipation off. So turn off the dissipation. What you see very clearly is that the diagonal current doesn't change, but the direct current vanishes as we switch dissipation. This points to the fact that in a direct configuration, for example, connecting the electrode to C and G, we are actually measuring dissipative current, inelastic current, no matter how we call it, but it must have dissipation in it. In diagonal, it's actually unaffected by dissipation. So what is going on here? Let's look at the system. We have, as we said before, a C band and a G band. For whole energy, the C band is higher in energy. If we connect diagonally, so C to C, we actually measure direct transport or coherent transport through the C band. Okay, we enter at C, we go, as we went before in the Landauer calculation, just take one orbital and go all the way through the molecule. On the other hand, if we switch to connection to C and G, the only way to get from C to G is to enter to the C band and then inelastically go to the G band. So once we switch off dissipation, of course, we block this inelastic channel. Okay, so that explains what we see in a direct connection. We do measure dissipative current. But maybe what's more intriguing, why don't we we have dissipation. We put on dissipation explicitly in the system. We connect diagonally, so C to C, and the system doesn't seem to care if we have dissipation or not. So we are measuring, if you want, coherent transport under dissipation. How does this work? Why does this happen in this system? And this is, okay, to see this, let's look again at this diagram. So in the inelastic case, where we go from C to G, we enter to C, we go inelastically and leave at G. So C is coupled to the left electrode and not to the right. G is coupled to the right electrode, not to the left. This is a legal passage. If we go to the diagonal connection, where we go from C to C, suppose we have inelastic processes. Suppose we enter to C and now go down to G. How would it affect the current? It would not affect the current, at least in this model, since the G band is actually not connected to either one of the electrodes. So any charge, in this case hole, any hole that gets into the G band is really left as charging and accumulates there. So this inelastic process is blocked within a sub-picosecond time scale. So even if you allow formally elastic transitions, your connectivity strategy to the electrode means that you're actually throwing electrons, or hole in this case, to a trap, and the process will be self-terminating. So even though you have dissipation under certain condition, you will not see it. You can still measure coherent transport. So that's our explanation here. Yes.
Determinative for the exclusion principle, why will determine?
Yes. Pauli block.
Okay, Pauli blocking. Sorry.
Yeah. It was just the last minute. You know?
Okay.
So if it was electron, it would be Pauli blocking. For holes, it's the analog. It's just charging, I would say. So that's in the spirit of Pauli blocking. Yeah, you can see that the inelastic current also depends on temperature, and the coherent transport is independent on temperature. This is going to room temperature. Different sequences of similar symmetry and similar connectivity give the same. I don't want to dwell on it. And I want to conclude this part of the talk. For proper molecular order, symmetry, and connectivity, coherent ballistic charge transport through DNA should be measured in spite of the dissipative environment. The mechanism for this is blocking. This blocking that I mentioned for some connectivity, pre-designed connectivity and sequence structure. Even though you have inelastic processes, they will not affect the current. That's the idea. This is due to this blocking idea.
Excuse me, but if you increase dissipation,
yes,
then you may have also some contribution or not?
Okay. All I said, this is a very a good point. Everything I said is about weak dissipation. Okay. If I have specific nuclear modes, as we heard in the last talk, which are strongly coupled, I must embed them into my system, my vibronic system, and do the calculation. Everything that is weak will actually will fall into this description. Anything strong must be handled properly, not with red field or anything like this. Okay. So how much time do I have? I need to...
Okay. 8 minutes.
8 minutes. Ouch. Okay. Let's see. Okay. So this until the 40 minutes? Okay. I will try to...
You have 33 minutes already.
Okay. So let's continue to work. Wake up, those of you who don't like DNA. The second part, I will try to be very brief, is about using molecular coherence, coherent electronic wave packet to induce charge pumping. What is the idea? The idea is that we will make some coherent excitation and make current flow in a given direction using molecular asymmetry, even in the absence of bias or sometimes against bias. So how can this work out? Our proposition is to use an asymmetric molecule. Suppose you have a molecule with 2 chromophores, 2 pi systems separated by some sigma bridge. So it's an asymmetric system. For us, this asymmetric system is modeled onto a 3-site model. But now we model an exciton in each site. So this is this chromophore. These are the homolumo. And this is the other chromophore, the homolumo. And this is the bridge. What's important for this little single molecule pump to work is to have asymmetry. So the homolumo gap must be different between the 2 chromophores. But either the homo or the lumo should be nearly degenerate. Be with me on these details. So once we define the system of 3 sites, 2 of them are homophore, different but with aligned homos or lumos, we can put the electrodes in. And so this is the Hamiltonian. Let's not dwell on it and think what will happen. So suppose we have just 1 electrode and 1 chromophore. This is a homolumo excitation. We created an exciton. And now what will happen normally if we just have 1 electrodes? We will have relaxation processes. If you want, there's energy transfer to electron hole creation in the lead and then equilibration in the lead. So we have a single event of energy transfer, electron here, hole here, things die with some relaxation timescale gamma. But now we devised a more interesting system. We have another chromophore here. See, this chromophore, as I said, must be in resonance, but in either the homo or the lumo. Suppose it's in the lumo. This resonance implies that there will be an efficient charge transfer, not energy transfer, but charge transfer to this right chromophore. Since these are not, the asymmetry implies that these are not in resonance, so hole will not be able to tunnel to the other chromophore. Okay, so what we propose here that will happen, there will be exchange, super exchange as it's called, or tunneling between the two chromophores, and then this electron has the chance to go to the right electrode, but this hole is localized. This is a process of, if you will, an exciton splitting in one molecule, a bichromophoric molecule, because the net result will be that part of the electron, with some probability, the electron that was excited, the exciton that was excited will give left to right current. So again, this is the scheme. How this will be reflected in an experiment. I think we heard about this in the talk by Gurwitz. We can measure, we can think of a measurement. The measurement here is just the current. So we can measure transient currents. There is a left current and a right current, and this can be calculated within this density matrix approach as I described before. I want to show you that these currents are really related to intramolecular coherent motion. So let's consider a case where the time of the tunneling or the super exchange time, tau, is of the same order of the 1 over the decay rate or the relaxation rate. In this case, what you see, if you follow the current, you see a current going from left to right. Positive is what enters the molecule. Negative is what leaves the molecule. You see very clearly that there is after the sudden excitation, there is a pulse of current going in and out. Let's look at the internal dynamics. So put our observable on the chromophores. We can follow each one of these, not just the exciton, but the HOMO or the LUMO. And what you can see is a very clear correlation between the transient current and an intramolecular coherent transition between the LUMO of the donor, this guy, to this guy. Okay, one can control, I will converge to the end. One can control the time scale for intramolecular dynamics by the molecular bridge. So playing with the molecular bridge, we can reach conditions where the tau, the period for dynamics, is much faster than the decay time. In this case, the current will show bursts, several bursts of current going unidirectionally from left to right. And if we follow the dynamics, we see that any one of these bursts of current is really related to intramolecular dynamics between the chromophores. What really, okay, this is just to explain that the way to control the pumping efficiency is to play with the molecular bridge. The lower the molecular bridge, the more efficient will be the pumping. We also discussed vibronic coupling at the bridge. I will not dwell into it. And let's conclude this part, and maybe I don't have time for the other story. So coherent electronic dynamics in an asymmetric donor bridge acceptor molecule can be utilized for unidirectional electron pumping. Transient current reflect the time scale for intramolecular coherent dynamics. So if you want, we can actually measure the coherence in the molecule by measuring transient current. And the efficiency is controlled by playing with the molecular bridge. I will not talk about reservoir control, but I guess I just have no time, so I apologize for that. But there will be other opportunities, I guess. So let me just jump to the end. Actually, let me think. OK, what I did talk about is ballistic transport through DNA molecular junction under specific conditions. I described a coherent bichromophoric single electron pump that converts molecular coherent motion into currents. I did not talk about reservoir control of quantum transport. I want to thank my collaborators in this work, Daria, Ro'i, and Meital. And I want to thank you for your attention.